Okay, welcome to this year's Hsu Distinguished Lectures, 许振荣讲座. The Hsu Distinguished Lecture Series is the most important annual event for the Taiwanese mathematical community. And this annual series is held jointly organized by the Institute of Mathematics, Academia Sinica, and Taiwanese Mathematical Society, officially known as the Mathematical Society of Republic of China, since 2011. And so I will now ask the president of the TMS, Professor Minglun Xie, to say a few words about the Hsu Distinguished Lectures. Minglun.
Good afternoon, everyone. Let me give a quick introduction to the Xu Zhenrong lecture. So this lecture was established by the Taiwan Mathematical Society and the Institute of Mathematics in memorial of Professor Xu Zhenrong. Professor Xu Zhenrong was an influential Taiwanese geometer in Taiwan. And he was born in 1918. He received a PhD degree from Tohoku Imperial University in 1941 and came back to Taiwan as a faculty in the Department of Mathematics of National Taiwan University in 1946. And from 1965 to 1983, he was a professor at the Kansas State University. In 1981, he joined the Institute of Mathematics in Academia Sinica as a research fellow and retired there in 1988. Professor Xi was not only one of the founders in the early stage of the Department of Mathematics of National Taiwan University, but also a founder of the entire Mathematical Society of Taiwan. So these lectures are sponsored by the Institute of Mathematics and by a special fund of the Taiwan Mathematical Society through the generous donation from the Xi family. The society is deeply grateful for the support and the commitment from the Xi family. So today the Xi family, Ken and Carol, are not here, but I believe they will join us at the banquet of the Xi lecture today. So on behalf of the Taiwan Mathematical Society, it is my great pleasure to welcome all of you to the 2025 Xu Zhenrong lecture. Thank you very much.
Okay, so this year we're extremely delighted to have Professor Ngô Bảo Châu to deliver this year's distinguished lectures. So Professor Châu is a distinguished mathematician celebrated for his transformative contributions to number theory, representation theory, and algebraic geometry, among other things. He's perhaps best known to non-experts like myself anyway, for proving the fundamental lemma in the theory of automorphic forms, a pivotal component of the important Lagrange program, by introducing algebraic geometric tools such as Hitchin fibration, which we'll hear about again today. He successfully bridged harmonic analysis and arithmetic geometry. So his landmark achievements have earned him global acclaim, most notably the Clay Research Award in 2004 and the Fields Medal in 2010. So we are very honored to have him as this year's Hsu lecturer. In the first day of this series of 3 lectures, he will talk about generalized Hitchin fibration and orbital integrals. Let's welcome Professor Châu.
Thank you very much. It's my great honor to be invited to deliver these Hsu lectures for the Taiwan Mathematical Societies. I'll probably 3 talks, a completely different flavors, but they are all derived from Langland's program, of course. So the first lectures will be connected to my now quite own work 20 years ago on the fundamental lemma, Hitchin fibration. But recently I've been thinking about it again, so it has some kind of new interesting thing connected to that, which I'm trying to explain. So tomorrow my talk will be much more analytic flavors. So it's some it very much connected to the one of the last papers of Langland's about what he called the stable transfer factors. But now we are still very far from his dream. So basically what I'm going to do tomorrow very much like calculus on functional one variables. And then the last day when you talk about representation theories, geometric representation theory, how you construct representation using per worksheets and stuff like that. All right, so today I think it's quite nice to start the lectures. Last week, a couple of days ago, I was in India, so I started lectures with recalling some of the great theorem proved by Indian mathematicians. That was beginning of the so-called non-abelian host theory. It's the theorem of Narasimhan. Seshadri. So when X is a compact Riemann surface, and look at the fundamental group of X, that they have very nice presentations, and then you look at the unitary representation of fundamental groups, and this very much a topological object, but Narasimhan says how do you discover that they are in bijections with a polystable vector bundle of degree 0. Vector bundle. So now, of course, on this part it doesn't require the analytic structures, but this part of vector bundle depend on the analytic structures. So later on, this amazing correspondence have been generalized quite a bit. So if you, instead of representation in the compact group, unitary group, we look at the representation of pi 1 of X into G and ln of C. Then somehow it's not so intuitive at the beginning, but then it's very similar. The polystable Higgs bundles. So that consists of a pair of V and phi, where V is vector bundle of rank n over the curve X, and phi is so-called Higgs fins. And, it has something to do with Higgs particles. I cannot explain it, but I am told that it does have some. Is some kind of endomorphism of V twisted by the canonical bundle of X. So in other words, it's a map from V to V tensor K, and also satisfying this zero Chern class conditions. And so the representation that have unitary image correspond to the Higgs bundle with phi equal to 0, and that is this very nice correspondence. And this leads to Hitchin and other people, Donaldson, and this actually be generalized to not, it's not restricted to, it's quite amazing that it is such a very deep fact, but it actually not limited to 5 dimension 1. It works for any compact smooth algebraic varieties, and this is due to Corlett and Simpson. So the vector bundle with some Higgs fins, and now Higgs fin is a bit more complicated. I don't want to say what it is. But the thing that this is look like a connection. So this is a map from tangent of V to V, an action of tangent of V to V. But in the difference with the connection is it is linear over X. It's not there's no Leibniz rules involved. This pure algebraic object. All right. So now, so for me, this is purely inspirational. I'm not really using it anywhere. But let me try to somehow to can be generalized to reductive groups. So that now G also can be generalized to any G reductive group of complex numbers, and here phi is going to be a global section of X of the adjoint bundle of X, twisted by the canonical bundle. All right. So so now what is rather quite interesting is this is the Canona-Berian host theory. So this has quite a deep connection with the Langlands programs. So let me just copy something like this here. This part is the character varieties. So the classifying representation of pi 1 of up to isomorphism that you divide by conjugation here. So this has the character varieties. And by this bijection, which is actually the real analytic map, you have this into some M on the Condon-Boho moduli space is moduli space of Higgs bundles. So I'm ignoring all these kind of technical condition, polystable and zero Chern class. It's actually very interesting indeed, but for what I'm doing, I'm going to ignore it. So you see, that's only quite very interesting fact is that this space can be given algebraic structures. Right? The pi 1 is discrete group have generators, and then given homomorphism, it's just giving element of G such a condition and divide by this. So this can be parameterized by some affine space. It can be affine algebraic varieties. This moduli space is not algebraic, not affine at all, right? The main features of Higgs bundles is that it comes with symplectic varieties. It's complex symplectic manifolds, and it's given with the integrable systems, complete integrable system that has as many Poisson commuting functions as as a half dimension of M, and more concretely, you have this remarkable object called H from M to A. It is called Hitchin fibration. And you'll be disappointed. Actually, very simple things. It's nothing complicated when you have endomorphism of vector bundles, and then as endomorphism we have characteristic polynomials. And this map is just, to recall the coefficient of characteristic polynomials. So this is, if you have E and phi, this is going to map into A is going A1, A2, AN, where AI is a section of K to the I, right? Because when you check the trace of wedge I, is the trace of wedge I of phi, then it's going to be a section of, the I powers of the canonical bundles. So this is just a large vector space. This is the complete algebraic fact, but it takes more work to prove that this is actually Poisson commuting. And what's kind of amazing fact in this space is really the half of dimension of M, right? This is all right, and as as any integrable system, genetic fibers are tori. And in this case, genetic fibers are actually abelian varieties. There's some component involved, but it's actually abelian varieties. And so we see the kind of difference, because in M you have many abelian varieties as subvarieties, and a phi algebraic variety cannot contain abelian varieties. So this one requires interesting fact. So now, what was it's going to come back to the work of Narasimhan, from the very important paper by Narasimhan and Harder Narasimhan, where they, back to, 40, 50 years ago, where they calculate the Betti number of the moduli space vector bundles by counting the number of vector bundles over finite fields, right? So you can very well try to do this counting exercise. So now here on this buck we leave a C. So now if you go to some finite fins, just try to change to finite fins, and then doing this counting exercise, so you just count, giving a curve defined over finite fins, then you just try to count this object, a vector bundle with the two endomorphisms, very much in the way that how the Narasimhan count vector bundle alone. You just have this added to phi, and then almost without so much effort, we found that the M of FQ is very much like what we call a very familiar object in automorphic forms, called the orbital side of the trace formula. For Lie algebras. I'm going to write a precise formula, but not just. And also what is this very pleasant is if you count the numbers of a point over some A, some given A, then it fits very well in these pictures. This is called the the sum of orbital integrals. In some stable conjugacy case. So you don't have to worry, but I'm trying to write the precise formula this later. So what happened is, in automorphism there's many kind of different trace formula. But here the point is that the trace formula for Lie algebra is the most simplest thing. There's a much more complicated trace formula, but somehow we are lucky that the Hitchin fibration corresponds to the simplest trace formula that can handle the trace formula. So for example, the Rhion trace formula is so now it's not a really short analogy. You have the trace formula, the bona fide trace formula. You have the Arthur trace formula. So it here it just gives similar formulas. Right? It's not the same object, but you can come back to this, and that would correspond to what I call the multiplicative Hitchin fibration. It's also one object that people in moduli space studying quite hard. So this is and actually there are a lot of different trace formula for relative trace formula. They all fit into this scheme. They're going to all correspond to different kind of Hitchin fibration. This is kind of the thing that I want to explore. So because in my work 30 years ago, I stay within this part of the trace formula Lie algebra. So we'll come back to that later. So, but before to go into more technical things, I just want to complete this diagram. So, on the open side of trace formula, there's some kind of spectron psi, right? Now the spectron psi has to do with automorphic representations. And now they are by Langland conjectures. They are classified by something like pi 1. Of course, not the same pi 1. Here is the topological pi 1. Here is the algebraic pi 1 with value in G duons. Right? Automorphic representations classified by this. So which kind of rather fascinating that we start with something pi 1 in G. You go along on this kind of complicated, a bit zigzagging road, and you end something very similar, but it switches the group G. So I don't claim that I can draw any conclusion from this, but at least there's some kind of very concrete fact that probably the most important fact is this Hitchin fibration theory was discovered by Hitchin. With that, the Hitchin fibrations for G and for the duon group, right? You can assume the split group like SP2n and SO2n plus 1 are actually dual. A duon abelian fibrations. In the sense that this is not very precise, but the part is very precise. That as unique fibers, you have dual abelian varieties. And singular fibers is develop something more complicated. But on unique fibers, it must be canonical dual abelian varieties. So this very fact is really I think it's not. This was observed by Hitchin and proved by other people, and Donaghy Pantev. Over C and over finite fin was proved by Chen, your Taiwanese fellows, Southern Chen and Zhu. They proved this thing over, I think the finite characteristic. And I think this fact is really some of the most simplified and geometric fact that have some classical limit of the Langland correspondence. All right, any questions before I go to something more technical? No. Yes.
Naive, the Hitchin vibration is a vibration, right?
Well, no, it's not a vibration.
It's not a vibration.
It's a map. It's just a map, algebraic map. On the there's a locus, so it's abundance varieties, and there it is a fibration. But there's a lot of singular fibers, and the work around fundamental lemma is specialized to study the singular fibers.
Where is it singular? Is it like it's like the
Yeah. So you see this. Look at this. You have when you have the let me maybe draw a picture here. So this is your curve, right? And you have this is your cotangent bundle. And every time when you have this A1, A2, AN, you can just write the Cartesian polynomial, then that gives you a finite cover, right? With a spectrum cover. Right? This is a real equation, yn minus A1, yn minus 1 equal to 0, and y is the kind of vertical coordinate. It really makes sense for this AI section in the power of canonical bundle. And this is YA, right? And it is known that Hitchin, that is what discovered Hitchin by when this curve is smooth, it can it doesn't go to ramification, but if the curve is smooth, then MA is pika YA, right? So there it is a fibration as long as this curve is smooth, right? But now you have a kind of a linear system of curve, right? The generic curve is going to smooth, but then when you can get to some singular curve. Yes. Yes. It can be reducible. It can be even non-reduced. Right? So it can be anything. All right. So this is the. All right. So let me say something here. Is the my work a long time ago was about in this trace formula, both from the multiple trace formula or the additive trace formula. There is a very, very peculiar feature called endoscopy. That I don't have time to explain what it is. Really, it's some arithmetic property, some Galois homology related to that. That takes quite a while to explain it. But what is kind of really nice is when it took me really a while, but that endoscopy, which look very arithmetic here, must have some geometric counterpart here. So what is called geometric endoscopy? So there's some, you can say what is geometric endoscopy on Hitchin fibration, which was not actually the people doing moduli space didn't know before. So from the arithmetic, you can actually discover some new features of even of the complex numbers, and then you can use geometry to go back and to prove, and then this go like this for definition, and it go like this for give you this, give you a definition, and that give you a proof on the fundamental lemma, right? So what is this geometric endoscopy is about? So this basically you have here the trace formula. Here there's some kind of trace, so maybe so now let me write some formula, right? And now the counting formula. Now K is finite field, then MA of K is going to be a sum over gamma in G of F. Now F is the field of the rational function of the curve. So some conjugacy class of gamma. and orbital integons of some test function so this is exactly the kind on the trace formula. Here I just want to the term that I have not defined what 1D. D is a canonical divisor. So so we write K as O of D. Right? You choose some non-zero meromorphic differential and write K as O of D. And then 1D, so A is addense and 1D is a test function. A characteristic function of P V minus D VG O V. I don't want to go too much, but you can design a test function so that the trace formula for that test function is exactly this counting point. There's one and one more to be not to say something wrong. Have something like this here. Some sum over K1. So this is some Galois cohomological thing, some class which is trivial locally. So C had to add C everywhere. But the thing is this the appearance of this term actually simplified thing doesn't get that on your way anytime. So we can basically ignore it if you wish. And then this is M and MA. You read the same thing, but here is a gamma that map into A. The gamma given characteristic polynomial. All right. And so the endoscopy tell you that this sum here really some exercise about Galois cohomology, because even when the characteristic polynomial is fixed, there may be more than one conjugacy classes. Right? That is kind of basic Fermi endoscopy. Actually, for global fields, there are infinite many. When you constrain by the test function, only finite many survive. But this kind of rather complicated thing. But at least this sum is, the Galois cohomology when gamma regular semi-simple, it's controlled by some torus, and you have some abelian group here. So here, this endoscopy say the former sum can be developed as sum over some kappa inside some maximum torus, some addition things, and some term, parameterized by kappa. So this is some dual group of the complicated Galois cohomology could appear here. And for the sum of our own thing, you have to sum of a kappa in the conjugacy class is the Lagrange dual group. So again, this the whole thing. You really don't want to go into detail because you are completely lost. So the only feature that you really want to know whether what kind of how to index the sum. Right? So this sum is completely canonical. So we really want to understand how with this endoscopic decomposition, which is so important in Langland's problem, how does it appears here in Hitchin fibration, right? Because it basically the same, right? Now the kind of obvious answer is you want to H it is mapped from M to A. Also, by the way, here's I'm cheating quite a bit because this form doesn't make good sense. It's just some kind of bijection because both sides are infinite. Has some kind of bijection, but it's infinite. Although this part can be finite. For when A is regular, it is a finite sum. So this is a bona fide formula. This is really motivational. So, but anyway, the only explanation of this is that when you look at the Hitchin map over there, so let me write over here because I think it's important. This thing is that A star of QL, to take the over finite field, you do LD cohomologies, and the push forward of the constant shift. Now the thing that counting point by point should be written as have canonical decomposition. Right. So there must be canonical decomposition of cohomology of Hitchin fibration. Just derived from, by analogy with the trace formula. Here we have canonical decomposition, so here there must be one. So we have to understand how to decompose this. So in general, you see when you have decomposition like this, it needs to have some group action. Right? So what is a group action? What is the theta that act on Hitchin fibers? So this is the question now. What are the symmetry of the Hitchin fibration? So now come back to this case. Of course, here it is almost a group. It's a pika variety, so it's a groups. So, but when YA is singular, then MA is no longer pika varieties, but called the compactified pika varieties. We classify torsion free shift, right? And somehow this description of pika and pika only exists for GLN. We are interested in other groups, it's become very complicated. Sometimes it exists, sometimes it doesn't, right? But the common feature here is, it seems to be very simple here, is you have the pika of YA act on compactified pika, right? So we don't really have to understand this. This is called the harder bovine Narasimha-Ramanan, the description of Hitchin fibers as some compactified pika. But we just keep something very simple that the pika act on the compactified pika. And so we have to understand what the pika in general, right? So this is, so what we want to understand is we want to construct a group scheme P over A that act on M. So the PA act on MA in the same way that pika act on compactified pika, right? And so if you have this, then you have the pi naught, well, the PA acts on the cohomology of the fibers, and by homotopy argument, it acts through the group of component, right? Pi naught of PA, right? So this pi naught of PA is quite not interesting in the case of GNLAN because only in this case only to Z to the irreducible component of YA. So it doesn't decompose anything, but in general this can have a torsion. So what is really interesting is the torsion part of the pi naught of PA, and what you're going to see that decompose the cohomology of Hitchin fibers, right? So every fiber you have canonical group PA, and you have the component group and the torsion part component group. That will give us decomposition of Hitchin fibers. And also because this thing is smooth, this can behave in families. So we have actually decomposition in families. So it's no longer a dual group, but something more complicated because this is so this is not a group, but it's a set because you have the five. The pi naught of PA is not a constant group; it's a shift. But anyway, this is somehow I don't want to. What I really want to explain how to construct this P. Right? So this is really. So now the construct of the P, the construction of this P, they derive from very classical invariant theory. And that is the part of invariant theory I want to develop for two other situations that I explain later. Right? All right. So we see when you look at the definition of the Higgs bondons. Right? So Higgs boson is a pair of V and phi, where V is the G bondons over X, and phi is a global section of the adjoint vector boson twisted by the canonical boson. Right. So let's do this kind of stack key exercise to write this as reformulate it as a stack. What really counts here is the adjoint. So they have G is Lie algebra of G, and acted on by G by the adjoint action. Right. So the kind of the very basic core Hitchin construction is this action. Right. You have the Lie algebra and G adjoints. So with this you can form the stack key quotient. I'm not going to say it, but it basically do nothing much. But the Higgs bondons Phi just become a map from X to this stack. By definition, this is without the K. The map from X to adjoint V is really a map from X to this quotient. So now to take into account this, you have to twist it with twist by K. I don't want to. I want to forget about this thing. This is not relevant to my discussion, but basically, Higgs bondons is really a map from X to the stack quotient of Lie algebra divided by the group. Something had to be done with the canonical boson, had to twist it somehow. But so please allow me to forget about K. I don't have too much time to make everything precise. Okay, so let's just put K here. All right, and then what is the Hitchin map here? The Hitchin map is have to do with the other quotient, which is let me write it here. Called the category quotient or invariant quotient, which is the canonical object within the category of phi scheme, right? And this is just defined by the spec of the ring of G invariant function on the polynomial, right? This is, and so this is this is studied thoroughly in invariant theory, and it's the same as spec of K of T, the Cartan subgroup, the finite group, and this is also the phi space. Right? So all this are different Chevalier theorem. This is Chevalier, and this is Chevalier also. Different is Chevalier Tot right. So invariant function on G can be given generate independently by n invariant polynomials. So this is in this case are the coefficient characteristic polynomials. Right? All right, of course there's something to be worried about the degree, right? Because they have some GM action here, and they have different degrees that are exponent of the Lie algebras. Right? Anyway, so of course we have the map from G mod G to these things, right? So this is the V phi, and this is A. So the Hitchin map just contains of composing, right? So of course I want to choose by K here, and the setup map. So G mod G is a vector space. Twisting by K give you a vector boson, sum of Lie bondons, K to the power of exponent, and A is just a collection of sections of those things. Right? All right, so so this is the setup. So now we have turned Hitchin construction into something really invariant theoretic, which is a map from one to understand this map. Invariant theory. Now I want to understand this map. From the Stucky quotient into the invariant quotient, right? So invariant quotient is, you know, that the G mod G is on basically the set of orbit, the adjoint action, right? You check on orbit, and every orbit we remember also the stabilizers in that orbit. But G mod G is only semi-simple orbit, only closed orbit. And this map here is the sort of decompositions. So every element can be written as the sum of semi-simple and nilpotent commuting, right? And that is the map. So X equals XS plus XN. So semi-simple and nilpotent, they commute, and they should keep the semi-simple part, right? So this is the map, the very classical invariant map. So, but here we have something really nice in this situation is, first of all, semi-simple orbit is not very nice, right? If you look at semi-simple matrices, they do not form a new closed or open subvarieties. It's some kind of constructible subset. So what is much nicer is the G rec. Right? I have the G rec is the X in G such that the centralizer, the dimension of the centralizer is the rank of the group, right? As small as possible, right? Like one for nilpotent, this is one block, one Jordan block. And another way to say that for X is regular if Xn is a regular nilpotent inside the centralizer of Xs, right? So it just so happened that the set of regular orbit mapped into the semi-simple orbit right? This is bijection, right? For every semi-simple orbit, there exists unique regular orbit sitting over it, right? So this is so for the probably I'm going to remove this. I no longer need this spectral curve. So, but what is really important in this story is not just orbit, but also the centralizers, right? So we have this over G. You have the group scheme of centralizers. So every X is just a centralizer of X, right? So this is what the bad group scheme is not flat, but it's flat over G rec. So so this is actually smooth because the dimension is constant by definition over G rec, right? And then you have this map to the C for Chevalier of G mod G. So what is the very basic lemma in these studies? I was surprised that it was not found before. These things have to descend to this, right? So they have this unique smooth group scheme J over C such and plus G equivariant isomorphisms Let's go on this guy, and this is chi rect of chi rect star of J isomorphic to I rect. I'm just saying that this is using the G action, I can this thing descend to this. And moreover, this extend to here. It's no longer an isomorphism, but it extends to I. So first for the descent, which is not totally obvious, because if you choose the characteristic polynomials, then you can just pick some regular element of that characteristic polynomials. Now, if you choose two such regular element, then they are conjugate, right? So we can conjugate them, but the conjugation requires some transporters, some element that conjugate it. But the isomorphism doesn't depend on transporters, because the central is abelian. So that is basically the proof of this, right? So if you write in form, we have some double faithful flat descent, but with the argument what I told you, some identity to be proven, and the identity derived from the fact that the centralizer is abelian over the regular part. So this is the first part, and the second part is just some very basic algebraic geometry lemma, that is the codimension is more than 2, actually 3, and this is some phi things, and the normal thing has to extend to some phi. So we have some really nice, and then from this we actually have exactly what I just erased. So for every a in from x to g mod g in a twist, everything is GM equivalent, so we don't have to worry. Then you define J of A is A star of upper star of J, and then P of A, what I'm looking for is just the space of torsors of A star of J. So for G equal to Gn length, then you have this spectrum curve ya to x, and J of A is just a PA star of J of Gm, and P of A is obviously the pk of ya. So we have this is just a kind of more complicated group theoretic way to construct the pk of the spectrum curve. Right. So this gives us and this map give us the notion of PA over MA, right, by twisting. Right. So this is the construction. It's actually very elementary. It's very, very basic invariant theory. You have to look at on the adjoint actions, and there's only one thing to do with this. All right, and then of course to develop endoscopy, you have to now for every A, how to compute pi naught of PA, which actually varies quite interesting in an interesting way. Right? In the case of Gn length, it just depends on the spectrum curve can become reducible. Then instead of Z, it becomes Z2, Z3, as many factors as the irreducible component of the curve. But in other group, actually, it's very interesting. It can develop it can be generically trivial, and then it gets some Z mod 2Z, and Z mod 2Z times Z mod 2Z. It's kind of thing that can happen for classical group. And but this really requires the fact that you can have another description of J. So J here is constructed by descent from regular part, right? But the another description of J is by using the other Chevrolet theorem. So T is a Cartan, and this is a flat map, right, from T to C, and this is called pi. And J is basically, you have J1 is pi star. You look at the the constant torus over T, right? And then look at the push forward, and now we have this inherit some diagonal action of W, and take W invariant. So this is kind of very basic where you construct smooth group scheme by pushing forward very restrictions, right? Something flat. Now pi is flat. It's important to be flat. And now the claim here is J is almost 1 to J1. So there's a map like this, which is isomorphism on the neutral component. So they may differ on the connected component. So as a word, if you take J naught to be the open group scheme of connected component, then J is contained in J1 and contains J naught. So on the difference here is some sud on smallest in the finite group. But I don't even remember how to describe them, but their description. So that's how you can have a hand on J, right? And that is how you can compute this pi naught of PA, which is not easy, but when you have this, you can compute it. I just want to note that this is very important in the Langlands duality, the Chen and Hsu work, right? When you flip G to G dual, J1 flip to J dual not, and J dual not flip to J1. So the J and J dual are contained in between, and the finite group also flips. So we can use that to prove. It actually gives some slightly different proof of Chen and Hsu. Quite nice proof of Chen and Hsu. Right. So this thing is compatible with Langlands dualities. All right. So now, how much time do I have left? Okay. All right. So let me try to. What I want to say is what you want to study are the trace formula, right? And most of the time, it really the same setting works, but it just have some or other trace formula. They very much like you have M, some phi varieties, mostly normal, and action of G. Instead of the Lie algebra, it's basically any of phi varieties. Well, not any, but it's like it is some kind of symmetric space. This is the most close case, which have this kind of, when you know the notation, the P, K act on P, right? You have an involution, and K is a fixed point involution, and P is minus, it's odd minus space in this K mode on P. And if you do the same construction, then you got this called the Hitchin fibration for real and Lie groups. That is going to have to representation of pi 1 in some real and Lie group, not necessarily compact. So we have these very similar things. And for this situation, it's for me very interesting how to construct a group, trace formula, multiple group trace formula. Then you have some action of G on the Weinberg monoid. So it's a bit complicated object. You have a very simply connected group. There's some canonical monoid that know a lot about the group itself, and this gives you the multiplicative Hitchin fibration. And there's kind of radically more complicated situation is it's no longer trace formula, but had to do with Hitchin fibration for higher dimension varieties. Then this is some of 5 varieties, but it's very far from being normal. You don't need to know if they reduce. It's a map from like in the case of 2 dimensions. Then is the concomitant varieties. So in this case, both are smooth, but here the commuting scheme, we don't even know if it reduce. So it's much worse, but have also G option on here. All right, so we basically want to study what is you have the M, the stack M mod G, and the map into the M mod G. And here there's some kind of very similar to Chevrolet. Actually, this is not so hard. It can be the Chevrolet package actually generalized quite well due to Luna Richardson. There's some assumption to be made, but what I really need here to understand this map M rep mod G map into this, right? So here we are classifying closed orbit. Here you classify regular orbit, right? So regular orbit, because same dimension, you actually have a geometric quotient. And this is called the geometric quotient. And this is the Cartesian quotient. Right. So in the case of alternation, this map is an isomorphism. It has nothing to do. But in general, it's never an isomorphism. And now that is the kind of the point here. So this is been well studied by some of my students. This is Thomas Heimister. He described this map completely. It's actually not so bad. It is what happened is you can have something like this. Very much like the case of GM acting gx t minus 1 of y. So we save a copy of the Cartesian quotient, but then glue together away from some open subset. So you just have 2 copies, but the worst case can have 4 copies. And this is a symmetric space, can be described this way. So the case of Weinberg monoid, and this is done by my student like Jinggen Chi and Griffin Wang. They have not described in this way, but some of their work can be saying that this map also have the same features. But here it has much more copies, where there's some here there's something quite interesting in all this work. I ignore it. I didn't talk about. There's some constant section is very important. For group, which is important, is called the Sternberg section. But when you read Sternberg paper, there's something very bizarre. Is he choose an order in the among the simple roots, and they multiply matrix that orders. So it works, but nobody understands why there's this kind of order between the simple root. It doesn't matter. But then you can see here, right, on the boundaries, each of the choice give you one of the components. So the Sternberg section actually gives the description complete of this regular quotient in this case, right? As many as order between simple roots. Okay, I'm running out of time, but I just want to give the punchline of this is in the case of this is much more difficult, right? In the case of G equal to Gn len, then it's no longer these pictures, but the regular quotient. In this case, the M mod G is the Chow scheme. Classify zero cycle on surface on A2, and you have M the M reg mod G. This is not a scheme. This algebraic space, but it contains a scheme which is Hilbert scheme. So this famous resolution Hilbert to Châu is a special case of this construction. So it's an open subset which realize this map, right? So by conjecture, actually this should work on AV group G. For AV G, there should be some open subset of M reg G, which is resonant singularity of the Châu scheme for other reductive groups. And in general, the thing is this: when you look at the simplest action is Gm acting on some vector space, right? And then in that case, the regular the Cartesian coordinate is at a point, right? But the regular coordinate is projective space, right? So my conjectures, I'm not a conjecture because there's some counterexamples, but in many cases, unless you try hard to do it, you actually get a map which very much like something which is contain a projective space map into this. All right, I think that I'm going way over time and stop here. Thank you.
Are there questions for Professor Châu?
Yes.
So, like in this picture in the middle,
Yes.
so is it saying that the Hitchin fibers for G and G dual are almost exactly the same?
Well, generically they are dual and abelian varieties, but there's the sudden thing is it's not it's a algebraic start, right? So even on genetic fibers, it have some isotropy group, it's kind of finite abelian groups, and it has the pi naught, right? The pi naught, the component groups, and you go from G to G dual. So abelian variety become a dual abelian varieties. The pi naught become the isotropies or dual isotropies, and the isotropy become dual the pi naught. So that is the what genetic fibers. And you go to singular fibers, it's no longer the case, right? But what happened is in the kind of fundamental lemma side, if you take if you key on this pi naught things, you just keep the pattern on the pi naught arc trivially, right? See the cohomology of any fibers and look at the way pi naught arc trivially, that is a stable part, and they're actually isomorphic from G to G dual. That is one of the fundamental lemma, predicted that, and it is true. But it's really on the level of cohomology. There's no longer any relation between. There's no bijection whatever between the fibers. It's only on the cohomology.
More questions?
May I ask, should I think of SQ as in the context of relative Langlands, or
Sorry?
should I think of SQ as in the context of relative Langlands?
Yeah, of course, yes. Relative Langlands it should exist, right? Yeah. So, for example, you have two Spherical group, right? H1, H2, and then look at G acting on G mod H1 times G mod H2. And that is exactly the relative trace formula that you have to look at. Yes. And there's a lot of things you have to do, but for me, the first thing you have to understand this map from the regular quotient to a categorical quotient.
Do you think this geometric endoscopic decomposition can be categorified to the right category for the machine?
Maybe, but I have not thought about it. Yeah. Yes.
So in this situation, right, both the Hilbert scheme or the projective space, they are quotients which are like GIT quotients. So you pick some linearization, which in this case is just a character of the group, and take semi-stable points for that, and so on. So of course, if the group has, like the character group has rank 1, it can vary much. But if it's higher rank, then you can get lots of.
Yeah, I mean,
GIT
this is
quotients.
possible. That's what what I've been trying, but I couldn't. This is I think it's a conjecture. I'm pretty sure about this. There exists this the kind for M is the commuting varieties, then regular part is commuting regular pairs,
Yeah.
which is the smooth
Yeah.
part of. Then take the regular quotient. It's not the space of orbit. It's really some geometric quotient. Then this map is a conjecture. It is universally closed. So that is the existent part of the valuative criteria for property is satisfied. And moreover, there exists an open subset which is proper, and it resolution of singularities.
Projective.
The projective map.
Yeah.
Yeah. But I don't know. Professionally, you should think that there exists some lie abandon, and but I couldn't find as a lie abandon so far. But
Yeah.
but I'm not saying that it does not exist, but it's not obvious. But the proper scheme it does exist. For symplectic group, it can be done by hand, but
Also, so if you consider now the maximal torus in G acting on M, and you try to repeat the construction, can you try to understand?
you mean Chevalier construction.
Yeah, in terms of basically taking wild group
Yeah, that is going to be
action
here.
and
Here is T times T mod W, and it is not. But it's no longer proper. It's no longer smooth, no more regular. Right? Here the Chevalier version is this is T times T mod W, right? One copy of W. So that is not proper. It's not smooth, and this Hilbert scheme is meant to give you a symplectic resolution of that thing.
okay, wait.
Okay.
I can ask later.
Okay. Sure.
Say that.
Any more questions? Okay, if not, let's thank Professor Cho again. As announced, tomorrow the same time, and there will be a new lecture on a slightly different topic. Okay, see you tomorrow.